Hey Ramblers! This video covers chapter 3.9 in our textbook and deals with what's called the linearization and the derivative. Now that might sound very new and pretty extravagant, but a linearization is just something we've been doing for many sections now. We've been finding a tangent line. Well, in this section we changed the name of tangent line to the linearization. And we're going to use that tangent line to estimate the value of a function. Okay, I want you to take good notes, to pause often, and I want you to pay special attention how the linearization really is just the tangent line in a different form, where we just move some of the terms around. Okay, thanks for watching, and I hope this helps. Let's start off talking about something we already know how to do. Suppose I asked you to find the tangent line approximation, or I should say the tangent line to the graph y equals the square root of x at x equals 1. Why don't you take a minute, pause the video, and come up with the tangent line to the curve y equals root x at x equals 1. Okay, you know that all year I've been emphasizing that we use point-slope form, and we've finally gotten to the part of this course where you're going to see why. If we started to fill in the parts of the point-slope form that we need, namely the y, the x1, and the slope, we would get y minus the square root of 1 equals the derivative at 1, which we'll figure out in a minute, times x minus 1. Well, let's figure out what that derivative is. Well, y prime is going to equal 1/2 times x to the negative 1/2. And let's simplify that. So we get 1 over 2 root x. Now, if you evaluate that when x equals 1, that equals 1 over 2 times the square root of 1, which is, of course, just 1/2. So, if we simplify this, we get y minus 1 equals 1/2 times x minus 1. And that is our linearization. I'm sorry, that's our tangent line approximation. Now, to look at the linearization, all we're going to do is move this y value that's on the left side to the other side. So we're going to get a linearization which would be y equals 1 plus 1/2 times x minus 1. The linearization and the tangent line are practically the same thing. They just move this term on the left over to the right side. Okay, let's take a look at the graph of f of x alongside the tangent line approximation, or the same thing, the linearization, and we can compare the two. Okay, if we were to take a look at the graph of the square root of x, and if we were to look at the tangent line, now we just determined what the equation of that line is. That's y minus 1 equals 1/2 times x minus 1. And the idea of linearization is that we're going to try and estimate points that are close to 1, like 1.1 or 0.9, without having to plug them into our original function. Instead, we're going to figure that as long as we're close to 1, anything on this line will be close to the real y value. That if I'm on the white line, that's awfully close to what the value is on the yellow line. But as you can see, a line is much easier to calculate with than functions. Now, we're using a pretty simple function here, but imagine some of the more complicated ones that we've been taking the derivative of, and you get the idea. So let's also look at the parts of our tangent line and compare them to the linearization. All year, we've been looking at the tangent line as y minus y1 equals m times x minus x1. When we start talking about the tangent line, we use different terms in different places, but it's essentially the same thing. So the tangent line becomes the linearization by changing a few terms. Y sub 1 becomes known as f of a, and our slope m becomes f prime
of a. And what had been x sub 1, well, that becomes a. They also move y sub 1, as I said previously, to the other side. So we end up with a linearization looking something like this. Y equals f of a plus f prime of a times x minus a. And that is your formula for the linearization. Now be careful. This will also be sometimes referred to as L of x, the linearization. But under either name, this is the expected formula, and all they've done is just taken the tangent line and moved the y value over to the right side.
Okay, here's another picture of a curve with a tangent line to it. And again, now we're going to call this the linearization. Often they'll refer to it as L of x, even as another name for the linearization. And it's just the tangent line. And we've always been talking about, I'd give you an x value, and now they're calling that a. And then you'd go out and find f of a, and of course you'd find the derivative, f prime of a. And when you did, you would generate the equation for that line, which would be tangent to the given curve. Well, now we have just called this the linearization, and we're going to use it to calculate the values of function values that are near the given point A. But instead of actually calculating it using the function, we're going to calculate it using the tangent line. Yes, there's going to be some error. We're not going to bother calculating in this class what that error is. I just want you to be aware of the method of using a tangent line. Okay, let's take a look at an example, and then we'll wrap things up. All right, so they're asking us what's the tangent line approximation for f of x equals sine x near x equals 0. So all along we would have done this: y minus y1 equals m times x minus x1. And right off the bat, we know that x1 is 0. And y1 would have equaled the sine of 0, which, as you all remember, is 0. So all we'd really have to find is the derivative at 0, and we'd have the slope. So what would that be? Well, y prime is going to equal cosine, and since we're at 0, it'll be the cosine of 0. And I'm sure you may remember from last year, the cosine of 0 is 1. So we get this pretty simple linearization. That's just y equals x. And sure enough, if you zoom on a calculator, you can see, this isn't a calculator that I'm zooming in on, but you'll recall that the sine curve comes up through 0, and sure enough, if you zoomed in close enough, that would look like the line y equals x for a short period. Now obviously, sine starts to curve, whereas our line y equals x would keep on going straight. So at some point, the points on our line would get pretty far away from the points that are actually on sine. And so the farther we get from our center of linearization, or the given x value, the less accurate the estimate becomes. Okay, let's try one more example, and we'll use Zaption for that. Okay, as our second example, let's find the linearization of y equals square root of 1 plus x near x equals 0. Okay, why don't you pause the video for a moment and give that a shot, and then we'll come back and we'll show you how to do it. We're taking it from a tangent line to this new thing that they're referring to as the linearization.
Okay, so once again, moving from the familiar to the new, we have y minus y1 equals m times x minus x1. And in this case, our y1 is going to equal the square root of 1 plus 0, which is just 1. x sub 1 is going to equal 0. And to find our slope, m, well, that's just going to be the derivative. So we will have 1/2 times 1 plus x to the negative 1/2, which simplifies nicely to 1 over 2 times the square root of 1 plus x. Now, if we evaluate that at x equals 0, we get 1 over 2. So our tangent line would be y minus 1 equals the slope 1/2 times x minus 0. But as we convert that into the linearization, once again, we're going to move this 1 to the other side. So we get y equals 1 plus 1/2 times x minus 0. And you might see that called, just as I've said, L of x equals 1 plus, and they might simplify this and just leave it as 1/2 x. Okay, Ramblers, that's how you attack these problems. And once again, the formula for the linearization is L of x equals f of a plus f prime of a times x minus a. So let's make sure that's in your notes, and we'll start using that in class. Thanks for watching.